Talk about detecting protostellar luminosity outbursts with far IR monitoring. And I'd like to thank the organizers for putting me on the agenda today. So let's discover our origins. Protostars reveal the origins of solar systems. And with protostars, we're really looking at the very beginning of the solar system formation process. When I say protostars, I have something pretty specific in mind. Namely, there's still a dense infalling circumstellar envelope present, and that really dominates the observed properties and subsequent evolution of these systems. We think most of these protostars have disks already. ALMA is starting to show that that's the case, so this is really where you want to look for the earliest stages of protoplanetary disk evolution. And importantly, this is when the vast majority of the stellar mass gets accumulated. When young stars emerge from the protostellar phase, they're already more than 90% in place. So this is really the era of the major mass accretion phase. And as far as we can tell, the ages of protostars, the envelopes take 500,000 years to go away. So we're looking at the first 500,000 years of the star formation process here. And I'm going to tell you about what we did with Herschel and how that transitions into what can be done with origins. So I was part of the Herschel Orion Protostar Survey, and I want to tell you why we want to study Orion in so much detail. On the right side of the slide here is an extinction map of Orion. So what we mean by Orion is not just the Orion Nebula cluster here, but really the entire Orion A molecular cloud to the south and the Orion B molecular cloud to the north. Orion contains most of the young stellar objects within 500 parsecs. And it also has a range of star-forming environments. The three insets there are Spitzer images showing you what the environment looks like. When you're maybe in the first round of suburbs around the Orion Nebula cluster, you have a bright background, luminous protostars that are closely spaced. And as you start to go south in the Lin 1641 region, you start to get less bright backgrounds, fewer protostars, their separations are a little bit greater, they're less luminous, and then you really start to get out into the rural areas to the far south of L 1641, where there's very little background emission. So Orion gives us this full range of environments, and it's close enough to characterize what the individual protostars are doing. HOPS was a 200-hour open time key program. Most of that was imaging. We imaged over 300 protostars that were selected by Spitzer at 70 and 160 microns. We did spectroscopy of a targeted sample. And then Herschel was supported by Hubble, Spitzer, WISE, ground-based observatories. And I'll show you how all of those different data sets play into what we learned about accretion. So a key question that I want to look at is, how do stars get their masses? Now, there are a range of accretion intensities and accretion processes in protostars, but to simplify things, I want to talk about two distinct modes. This was first laid out in our Protostars and Planets paper a few years ago, the distinction between secular accretion and stochastic accretion. For secular accretion, we have the envelope gradually falling onto the disk. Maybe that rate of infall changes slowly over the course of the 500,000 year period. And then the disk accretes onto the star. And here, just for illustration, I show a Hubble image of a fairly passive protostar seen edge on, so all the different parts of the system are detected even in the near infrared. The alternative to this is stochastic accretion. You've seen this particular system in Kara's slides and maybe a few other times. Here we have a protostar that was nearly invisible when imaged with Spitzer MIPS at 24 microns in 2004. 4 years later, there it is. It really just winked on sometime between 2004 and 2006. So we have these two very distinct modes of accretion, where we have the sort of passive mode and then this very rapid luminosity outburst due to rapid disk accretion. These are kind of the protostellar equivalents of the FU-Ori stars, if you're familiar with those. So our main way of looking at this question with HOPS data is by looking at the SEDs of the protostars. These were all tabulated and modeled in the paper that Elise Furlan led in 2016. And here, just to illustrate, is a class 0 protostar at the very earliest stage of protostellar evolution. The green points and this gray spectrum are from Spitzer. You can see how Herschel in the far IR really fills in the peak of the SED. That's why you need that far IR data, so you can really estimate the luminosity well. And then at longer wavelengths, we had data from Apex to fill in at the submillimeter. That blue curve is a radiative transfer model we fit. From that modeling, we infer an envelope mass of 1.5 m sun in this case. The class 0 objects, roughly speaking, there's still more mass in the envelope than there is currently in the star. When we move on to class 1, now we expect the envelope mass to be less than or roughly equal to what's in the star. You can see how the Spitzer data are really picking up. Now the peak of the SED is slightly shorter than the Herschel PAX band passes. You still have your submillimeter data. Then we have this kind of transitional phase called the flat spectrum sources. Flat because throughout the mid-IR, the SED is pretty flat. Now you see the shortest wavelength detections are in the 2-mass bands. Herschel still gives us important constraints on the luminosity and the modeled envelope mass. And then our sample was focused on protostars, but nonetheless, we had a few stars that looked to be protostars based on the Spitzer data alone. But then when we started filling in the long wavelength part of the SED, they turned out to be class 2s. This is really the T-Tauri star phase where the envelope mass is negligible and you're left with a circumstellar disk in the central star. So with all these SEDs, and with the far IR data, importantly, we estimate 2 quantities of interest. One is the bolometric luminosity that we get just by integrating under the available data. The other is a bolometric temperature, which is a little bit less commonly used. This tells you something about the mean wavelength of the SED. We calculate the flux-weighted mean frequency, convert that into a temperature using Wien's law, and this is an evolutionary diagnostic. So the reddest, most deeply embedded protostars have bolometric temperatures of tens of Kelvin. As the envelope dissipates, the bolometric temperature rises through hundreds of Kelvin. Once all the circumstellar material is gone, or at least negligible, you're left with a bolometric temperature equal to the effective temperature of a cool star photosphere. So it's a way of tracking this evolution. For over 300 protostars, we can put all these bolometric luminosities and temperatures on a so-called BLT diagram. In the early 90s, this was put forth as a potential analog to a Hertzsprung-Russell diagram, but for protostars. Unfortunately, unlike for main sequence stars, there's not a well-defined main sequence. BLT diagrams have been constructed for many nearby star-forming regions, and you always see this scatter. So in spite of the broad scatter, we try to learn something about protostellar evolution from this diagram. There are 3 main takeaways from this. First, the broad spread in luminosities. If you divide the sample up into equal logarithmic bins of bolometric temperature, you get roughly equal numbers of protostars per bin. So that might tell us something. And if we take the mean luminosity in different bins, we have fairly high luminosities here, and then they sort of subtly decrease as the bolometric temperature increases and the protostars evolve. So we see these sort of 3 general characteristics of the diagram. We want to know, can we explain these with slowly changing infall rates over the star formation period, or do we need rapid bursts of accretion to explain the diagram? So we can get most of the way there with what I've been calling secular evolution. Here I've switched up the diagram a little bit. We've gone from purely observed parameters to parameters that we get from the radiative transfer modeling. We've gone from bolometric luminosity to total luminosity. That's really a correction for foreground extinction and anisotropic effects, such as, a protostar viewed down its outflow cavity will seem brighter than it really is, or viewed through its disk, it will seem fainter than it really is. So we've corrected for that. And then on the x-axis now, instead of bolometric temperature, we have the envelope mass that comes out of the radiative transfer modeling. That's the envelope mass inside of 2500 AU, because that's what the Herschel data are most sensitive to. These models I've shown, these are 3 sample models from an ensemble. What we do for our star formation model, we start with a range of envelope masses. And then we have envelope infall rates that are large early and decline exponentially. That's roughly what you would expect if the rate is the mass of the envelope that's remaining divided by the free fall time for that mass inside of that radius. And the consequence of this is we have luminosities that peak early as the stellar mass builds up, and then they gradually fall off as accretion slows down. So I've shown sample tracks for based on the final mass of the star that results. So this is a fairly typical stellar mass, 0.6 m Sun. This is kind of an intermediate to high mass case. We have a very low mass case. And the point is that a family of these models could span the space really well. If you have, and if you end up with what you would expect for an initial mass function of a cluster of stars, then you can, that's consistent with what we see in the diagram here. Now there are some signs here that we need outbursts to explain the model completely, to explain the diagram completely. There are more stars here with luminosities of a few to a few times 10 L Sun than you would expect if you were going to form a typical distribution of stellar masses in the end. So that's kind of an early sign of that outbursts are maybe important. And of course, we observe outbursts among our 300 plus protostars. Here on the BLT diagram that I showed you, I've used stars to indicate the positions of 3 of the outbursts. The stars are cases where we have full SEDs after the outburst. And then that arrow, HOPS 223, we have a pretty well sampled SED both before and after the outburst. So the arrow shows you how it moves through BLT space. The luminosity increased by about an order of magnitude, and the SED became a bit bluer because there was more high energy accretion being detected in the SED. We think that these outbursts are due to disk instabilities. You have gravitational and magnetorotational instabilities active in the disk. You have an envelope falling onto the disk, which causes its mass generally to grow over time. And that makes the disk more likely to go unstable and to form clumps. As these clumps fall into the star, you see this massive increase in the accretion rate and therefore the accretion luminosity. We have a series of models from Vorobyov and Albakian showing how that might proceed in a protostar. And ALMA images of particularly nearby, bright, young, accreting stars are beginning to turn up signs of these clumps that you might see from episodic accretion. What we want to do is to quantify the role of outbursts, since we're starting to put a large sample and a long time baseline together, and we can ask how much of a star's ultimate main sequence mass is accumulated in bursts. Here I've just written down schematically how the mass accumulated in bursts can be thought of as the product of the accretion rate in bursts times the number of bursts experienced while the star is forming times the typical duration of each burst. And we can look at our Orion sample to get a handle on some of these factors. To look for outbursts in Orion, we compared Spitzer data to WISE data. So we have Spitzer cryogenic observations of Orion in 2004, 2005. WISE came around in 2010. And you can see just schematically there are 3 Spitzer bands and 3 WISE bands that overlap pretty well. So we just did a comparison of all of our protostars in Spitzer to WISE. And we looked for sources that, over the course of 7 years, became brighter in all 3 bands while we were doing the comparison by more than 2 sigma above the mean variability. So that's kind of a bright line cutoff for outbursts. You could probably go back and look at more subtle forms of variability, but we were looking for like the really obvious cases to get a sense for how often that occurs. One of our detections was HOPS 223. This was more of a recovery. Its outburst was known before we did the comparison. It was discovered in near IR images. We did additional multi-wavelength analysis once we had the Herschel data in hand and some near IR spectra. It's far to the south of the Orion Nebula cluster in sort of the distant suburbs, and therefore relatively isolated. These are the before and after images, with Spitzer on top and WISE on the bottom, and you can see how HOPS 223 in the center there was basically the second brightest protostar in the field before outburst, and then it became much brighter than its companion in the intervening time. We have a broad data set here, so we can look at how the SED evolves over time. This is pre-outburst data from 2MASS and Spitzer. Integrating under this and extrapolating to longer wavelengths, we come up with 4.5 L-sun. We had a Spitzer IRS program that got a spectrum of this star in 2007 when it sat right there. We checked very carefully to make sure there wasn't an extra factor of 10 in our calibration somewhere. But we convinced ourselves that it really did get that much brighter in the span of 2 years. Subsequent data obtained from IRTF, we've got WISE, another round of Spitzer MIPS, Herschel, and APEX, all give us a roughly consistent SED over the period 2008 to 2012, where the luminosity was down a bit from what we saw with IRS. And we integrate to get 28 L-sun here, and a flat mid-IR SED, which indicates a low density envelope. This is a flat spectrum protostar. HOPS 383 is a little bit different. This was discovered by Emily Saffron when she was doing this comparison. She was an undergraduate at the time. This is north of the ONC in the very crowded OMC 2-3 region. It's very deeply embedded. You can see a near IR comparison there in the K-band. There's never a point source. After the outburst, we just see some of the surrounding regions illuminated by the light, but no point source. This one, not advancing all of a sudden. There we go. Here's the before and after, where it's nearly invisible in MIPS and then becomes very bright in the WISE 22 micron image after the fact. And here, if we look at the submillimeter data, it becomes brighter at submillimeter wavelengths as well. So this points to it being a true outburst. If it were just a change in extinction, say dust clearing and more light from the central star coming out, we would have seen a fading at submillimeter wavelengths. So this shows you how submillimeter data are complementary to the far IR. This is the SED. The cyan points are from before the outburst. We had very limited data. So this really highlights the value of far IR monitoring. Here we have just very limited pre-outburst information because this was so deeply embedded and faint before the outburst. And then when we bring in all of the post-outburst data, we can constrain the burst to somewhere between 2004 and 2006. And it's a very red SED. This is the first class 0 outburst to be discovered. So now we can look statistically, or start to anyway, how many bursts does a protostar experience? If we have 2 in 319 protostars in 6.5 years, if you just multiply this out, that suggests that every protostar should on average burst every 1,000 years. We've started looking backward before Spitzer. The McNeil's Nebula outburst that I showed a little thumbnail of a few slides ago happened just before Spitzer. So that's roughly consistent with this expectation. We have evidence now of a couple more bursts that were picked up in a final round of imaging with Spitzer that's in prep. And these continue to point to about 1,000 years between bursts. This means that if a star takes 500,000 years to clear out its envelope, it might have a few hundred bursts during that period. But we still have a large confidence interval. I'm just illustrating here how the probability distribution peaks around 1,000 years. The 90% confidence intervals go from a few hundred years up to about 40,000 years. This just barely overlaps with intervals that have been determined from similar studies of class 2 objects. So it looks like bursts are more frequent in the protostellar phase. That's consistent with them being driven by the infalling envelope at some level. But we want to go further than this. Those are pretty nasty uncertainties we want to try to beat down. We're also looking at the outburst timescale. SOFIA is a pretty convenient way to get not really time series photometry, but additional photometry while we're waiting for the next far IR mission. And we got mid-IR photometry of these objects with SOFIA in 2015, and they're consistent with the outbursts continuing a decade after they began, which helps us to pin down, again, how much mass is actually being accumulated in these. So what we need to make further progress on this is submillimeter and far IR monitoring. I have a white paper out where we outline a 2-pronged approach. We brought in some submillimeter folks to talk about the value of ground-based submillimeter photometry that gives us fast cadence monitoring at multiple wavelengths to track the progression of bursts. We have a light curve here from the JCMT project that Doug Johnstone and Greg Hertzeg are in charge of, where they detected a submillimeter burst. And then with the space-based far IR photometry, we would look at the long-term evolution of these objects. A little bit of a discussion of what we need to do this. Sensitivity is not really a problem. That top plot is a histogram of 70 micron fluxes of the Orion protostars in log space. They're all pretty bright. That's at 420 parsecs. You can sort of mentally shift that to 1,000 parsecs. And the sensitivities are all not really a problem for what's being discussed for FIP. Let's see. Another concern that we have is really mapping speed. The clustering of protostars makes small fields more efficient. So what we did is we looked at the 1,000 protostars roughly that we have inside of a kiloparsec and tried to figure out a smart way to divide these up into fields. The latest information we had is that it takes about 30 minutes to map a square degree field in one band. So most of the protostars inside 1 kiloparsec could be mapped in both bands in 10 hours. That's just what this plot shows here, is that if we choose these small half-degree fields, you could pick up almost all of these 1,000 protostars in 10 hours and do even better with a little bit more time. So if we ran such a program several times over a few-year mission, we'd have a nice little variability survey of protostars. Angular resolution is not a serious problem. Protostars are clustered, so at 5 arc seconds, we wouldn't really resolve all the multiple systems, but if you see something burst, you could follow it up with some other facility, perhaps a different wavelength that has better angular resolution. To really get the peaks of the SEDs, going longer than the 50 micron channel would really be ideal. So the 250 micron channel is, we're sort of bracketing the peaks of the SEDs with the wavelengths being discussed, unfortunately, but this would give us a lot more information than we have in the mid-IR, certainly. So this is just a little demonstration of how these uncertainties go down if you have long baselines and large surveys. So if we have a far IR surveyor launching in 2035 and compare that to the Herschel data, that gives us a 25-year baseline. So we can really start to look at the evolution of protostars over decades. And I wanted to point out, I'm talking about photometry of hundreds of protostars here, but these fields also contain more evolved T Tauri stars. There are, roughly speaking, about 10 T Tauri stars for every protostar, so this would be a great archival data set for people that want to study the time evolution of more evolved young stars as well. And I'm just showing here how this black curve is the plot I showed you before, where the upper limit is 40,000 years, the 95% upper limit. What we're working on now, where we found 2 more outbursts by doubling the time baseline, that already helps a lot. It brings the upper bound on the uncertainties down to 5,000 years. If it really is a 1,000-year interval for protostars, 1,000 targets with 25 years of monitoring would bring that all the way down to 1,500 years. So we would really start to have something with like reasonable uncertainties, so we can understand how important these bursts are for evolution. And just wanted to highlight, this is well suited to the capabilities of Origins. We're not like pushing into some really tricky technological space here. So that's what we're looking at. Just to summarize, with the Herschel work we've done so far, we already have broad wavelength and temporal coverage for over 300 protostars in Orion. Our attempt to explain all this scatter in the evolutionary diagrams, we think if we start with a range of envelope masses and have them form stars fairly quickly, we can explain most of the characteristics of this diagram, but outbursts are certainly important. We have an estimate that over 25% of the final mass of a main sequence star may be accumulated in outbursts like these. And long-term far IR monitoring is really essential to continue to make progress on understanding this problem. Just close with a list of my collaborators on HOPS and the white paper. These are kind of the main figures there, and thank you.